All right, so let's do bubble sort. These. I'm going to use the same list of numbers. Why did I? Okay. So bubble sort is probably the simplest conceptually, if you can imagine simpler than selection sort. Okay. The simplest coding. Basically, we're just going to say we're going to compare each two items in the array. And if they are in the wrong order, we're going to swap them. And we're going to go through the entire array doing that. Okay. If we do that one time, go through the entire array, swapping things if they are in the wrong order, what do we accomplish? You want to do it once? Let's try it once. Let me make a copy. So 82 and 55, swap, right? Everyone get what I'm doing there? Okay. 82 and 92, don't swap. 92 and 67, swap. Whoop. Okay, 92 and 90, swap. 92 and 38, swap. 92 and 15, swap. 92 and 53, swap. 92 and 96, don't swap. 96 and 35, swap. 96 and 43, swap. 96 and 60, swap. Yep. Okay, so that's one pass through the array using bubble sort. What did we accomplish here?
Well, I know you got the highest one in the right spot.
We got the highest one in the right spot. And I mean, sort of, I guess some of the idea behind it is we also sort of got the others more closer to where they're going to end up a little bit, right? Yeah.
Isn't it like sorting through, yeah, it's like sorting through the array, but only doing one at a time.
Only doing adjacent elements. Yeah. Okay. So then with bubble sort, we're going to say, okay, now that portion, whoa, that's not what I meant. Now that portion of the array has been sorted. So on the next pass through the array, we can stop one sooner. So let's do it. 55, 82, don't swap. 82, 67, swap. 82, 90, don't swap. 90, 38, swap. 90, 15, swap. 90, 53, swap. 90, 92, don't swap. 92, 35, swap. 92, 43, swap. 92, 60, swap. Now the second highest is in the correct position. The 92 is in the correct position. All right. Can you see why it's called bubble sort? We kind of each pass through, we're bubbling the largest one up to the top. I'm not sure if I could like explain exactly why that's bubbling, but it just kind of feels like bubbling, right? Okay, 55, 67, don't swap. 67, 82, don't swap. 82, 38, swap. By the way, you guys, you need to pay very close attention because if I make a mistake, you have to stop me. Okay. 82 and 15, swap. 53 and 82, swap. 82 and 90, don't swap. 90 and 35, swap. 90 and 43, swap. 90 and 60, swap. Now the 90's in the correct, whoa, what did I just do? I have no idea what I just clicked. Normal. Lucky guess. Okay, so far? All right, I'll try to speed this up a little bit. 55 and 67, don't swap. 67 and 38, swap. 67 and 15, swap. 67 and 53, swap. 67 and 82, don't swap. 82 and 35, swap. 82 and 43, swap. 82 and 60, swap. Now the 82 is in the correct position. $55 and 38, swap. 55 and 15, swap. 55 and 53, swap. 55 and 67, don't swap. 67 and 35, swap. 67 and 43, swap. 67 and 60, swap. Now the 67 is in the correct position. Right. It's going to go faster when I have smaller parts of the array to go, right? 38 and 15, swap. 38 and 53, don't swap. 53 and 55, don't swap. 55 and 35, swap. 55 and 43, swap. 55 and 60, don't swap. Now the 60 is in the correct position. Um, 15 and 38, don't swap. 38 and 53, don't swap. 53 and 35, swap. 53 and 43, swap. Whoa. 53 and 55, don't swap. Now the 55 is in the correct position. $15 and 38, don't swap. 38 and 35, swap. 38 and 43, don't swap. 43 and 53, don't swap. Now the 53 is in the correct position. Interestingly, we can see that the whole thing is sorted now, right? The basic binary sort doesn't check for that. But we'll talk about how we can actually write it so that it does check for that and it stops. All right, almost done. 15 and 35, don't swap. 35 and 38, don't swap. 38 and 43, don't swap. Obviously, there are going to be no more swapping, no more swaps. Whoa, that's not what I meant. So I can just and once we've got that, we don't have to go one more time because we already know that there's only one item left. It's sort. Okay. Any questions about the concept? I give you a piece of paper and 12 numbers. You could do this yourself. Okay. You may not want to, but you could. All right. Big O. Yeah. And you can pretty much intuit it by looking at the picture, right? I had to determine all of those numbers. I had to look at all of those numbers, and that's in squared numbers there on the screen. But just to reason it out, how many passes did I have to make through the array? N-1. Each time through the array, I had to look at least N, if not more, items, right? But however many I had to look at, it was related to N, right? Not N squared or something like that. It might have been, at worst case, maybe 2N. Because the reason I'm saying that is that sometimes I'm having to look at the same number more than once because I'm swapping it up. Okay. But we don't care about that constant. All we care about is that it's n. So we have to do something n times, and that something takes n steps in n comparisons. So the total number of comparisons is n squared. Okay. All right, let's look at the code. Wrong. So pretty short, right? I've got my for loop going from 0 to num items minus 1. So that means whatever's inside here, I'm doing it num items minus 1 times. So each time through the for loop, we're doing one pass. One pass means start at 0, go up to num items minus I minus 1. Does anyone understand why num items minus I minus 1? That just tells me where the end of the not yet sorted array is. Okay. So J goes from 0 up to the end of the not sorted part of the array. And then each time I just look at list of J and list of J plus 1. If they're in the wrong order, swap them. Done. Okay. I do get students sometimes who write this and they go all the way to the end of the list every time. And then they think it's a bubble sort. Nah, I'm getting mixed up with something else. Never mind. Any questions about bubble sort? How would we make it so that this stops if it detects that the array is completely sorted? So this for loop here, going through the array, swapping things if they're in the wrong order, we could say, what if it never swaps anything? Then the list is sorted, right? So that's what we have here, actually. I'm just going to say did swap gets true. Then instead of a for loop, I'm going to use a while loop because I want it to stop if did swap becomes false. No. Yeah, right. If I made it all the way through the array and I didn't do any swapping, then I want my loop to stop. So I set did swap to false. Each time through the array, if I do a swap, I set did swap to true. And so I keep going as long as I swapped at least one pair. Okay. Turns out if we run this code, it's not going to be any faster. You may be able to stop early sometimes, but that is more than made up for by the fact that every time through you're doing additional stuff, right? Every time through this for loop, you're having to do an additional assignment statement. So that slows it down a teeny bit, right?
Yeah, I ran this code with the 50,000 size and it saved like 79 milliseconds.
Okay.
50,000 swaps.
Out of, right, so 79 milliseconds out of
12,000. Oh no, it actually saved like 200 milliseconds. 12,881.
Okay. So that's actually like 10% or something, right? But it depends. I mean, you may run it again and it may be slower. I don't know. But
yeah.
The other thing is that you might want to do this if you have a situation where you suspect things may already be sort of roughly in the right order or something. Anyway. You guys want to do one more? 10 minutes left? I think we can do it. All right. No, lots of blank stares.
I was wondering, that doesn't affect the big O of that algorithm.
Correct, yeah.
Yeah.
It's just a constant that I throw in there. Okay, let's do one more. Insertion sort.